Welcome to my extra credit presentation. I choose the option with the KD tree data structure. So the problems to create the k-dimensional tree is imagine storing a location coordinates with x and y axis, and how would you sort them from the nearest to furthest, or let's just say to find the nearest specific point that you want to look for. We haven't learned about a way to store two-dimensional as a data structure in organized way. And that's where k-dimensional trees come in. A little bit of uh, historical context. The guy, John Lewis Bentley, he created he come up with the idea of the KD tree based on the BST, with the idea to searching through a multi-dimensional space, not just 2D X and Y, but many, many dimensions, as much as you can want. Some real world application for this data structure is they can use to be stored geographic information, coordinates, location, uh, database queries. So let's look for the nearest possible entries in the database, which database, they have many columns, especially SQL database. So you can put each column as a dimension and use the queries and use put them in this the KD tree data structure and query them to the nearest possible uh, answer that you would want. Some properties of the KD tree. Each node, they represent a k-dimensional point. So for example, in XY plane, each node would be a point. And they have a x coordinate and a y coordinate. Each level, they split the data along a different dimensions. So each each level here means at each height they split the data with the different dimension that have been set. It's very similar to binary tree structure with left subtree and a right subtree. The left point to the smaller value in the splitting dimension. For example, if the current level you're in is splitting on the x dimension, then you would compare the x dimension. If they're splitting on the y dimension, then you would compare to you compare it with the y dimension to be able to know where to go left and whether to go right. Is have an insert operation. Say the root node we have is 6, 3. Here I just do 2D sim I simplified the demo to 2D. So we have the root node 6, 3. Let's say I split the root node with the x-axis. Here we have a new node to insert it into 2, 3. So here we have, uh, for if we're splitting along the x-axis, then we compare with the x-axis, in this case 6 and 2. So 2 is lesser than 6, so we move it to the left. And here's a property of a KD tree that um, the splitting dimension, they rotates. So for example, we have the root node at 6.63. We split along the x-axis. Then the next level is the y-axis, and we come back to the x-axis, and we go to the y-axis. They go in rotation. And here we have another point, 8, 8. So at first, we will split along the go to through the root node, which is the split along the x-axis. We compare 6 to 8, and 8, 8 will go on the right side of the root node. We have another point, 4, 6. So as per our algorithm, we compare uh, along, we split along the x-axis, so we compare the x dimension, 6 with 4. We go to the right side, no, we go to the left side. And now we reach the y-axis level. We compare with the y dimensions. So we compare 3 with 6. So 6 is larger. So they go to the right of the 2, 3 node. And there you have, we got x-axis at the root node, y-axis the middle level, and x-axis at the leaf. So they just rotate. And we have another point, 5, 2. So 5 go to compare with the 6, 3 for the x-axis. We go to the left, and when we compare with the y dimension, we uh, for the y dimension, we compare 3 with 2, so we also move to the left. And that's basically the algorithm for the inserts for this data structure, KD tree. Next, we will explore one of its special feature, nearest neighbor search. It's a special property that the KD tree has support. So here we have a KD tree, and I graph the point on a 2D plane. So this is how they split up. We have 63.63, and we split along the x-axis. So we have x-axis is split along the x-axis. We have 23.23 and split along the y-axis. Same with every other point, 8, the y-axis, 5, 2, the x-axis, 4, 6, x-axis, 7, 2, also x-axis. Now we're going to find the nearest point to 5, 4. Let's say for this example, we considered all the nodes are coffee shop, and 5, 4 is where you are. So you want to find the nearest coffee shop. First, we will traverse to the leaf node using the 5, 4 coordinates. We compare 5, 4 to 6, 3 along the x-axis. So we go left. Next, we compare 5, 4 to 6, 3 with the y-axis. This actually wrong right here. It's not x, it's y. So we compare with the y. Oh, I'm sorry, there's a typo on the slides, but this is the correct one. We have uh, we're moving on to the 2, 3 node. So we compare our current position, which is 5, 4, to the 2, 3 node with the y-axis. So we take 4 and compare with 3. 4 is greater. So we move, so we go right, and we are at 4, 6. We have the leaf node. So we have 4, 6. We measure the distance between 5, 4 and 4, 6. Just standard distance formula or Pythagorean's theorem. And we have 2.236. Next step, we're going to backtrack to the parent node and check. So we backtrack to 2, 3. We measure the distance between 5, 4 and 2, 3. And we get 3.16. Next step, we will measure the distance from 5, 4 to splitting lane. Since the parent node is further than the best node that we found, the leaf node, the parent node is not the best distance. So we will measure the distance from 5, 4 to the splitting lane, just the y-axis, using the parent node, which is 2, 3. So we measured 5, 4, this point, to this line right here, to this point, which lie on the splitting plane of 2, 3. So we have 4 for the y, and we have 3 right here. So the distance is 1. And here we have two options. If the best distance is larger than the distance from plane, we go to the other subtree. Or if it's the other way around, we will ignore the other subtree. Sometimes people also say the other subtree got pruned instead of ignore. So in this case, we have the distance of 1 to the splitting plane, and the best distance is 2.2. So we will go to the other subtree. The other subtree in this tree here is the 0.52. So we measure the distance, and we have 2. The distance is 2. Next up, we also repeat backtrack. We go to 2, 3. Since we already checked 2, 3, we going back to the root node. So we measured the last one, the root node, 5, 4 and 6, 3. and we have the distance of 1.41, which is the best that we found. Since we already backtracked to the root node, so the 0.63 will be the nearest point from 5,4 to have no other node to check. The next topic we will discuss is complexity analysis. The KD tree for some operation, choose insert, deletion, and point search. They are very similar to a binary search tree, which will have an big O of log n if the tree is balanced. But we will make an analysis on the nearest neighbor search operation. The best case will be big O n log big O of log n, since it's basically like a binary search. Some situation where this could happen is if the queries find the shortest on the first leaf. So the first step to the algorithm is move to the leaf node. But if that leaf node is the shortest, then we don't have to find anything else. It's basically like a binary search. Worst case binary search. You have to move all the way to the leaf node n log n. No, not n log n. Log n, since it have log n depth. For the balance tree, most branch get pruned. So in the example that I talked about, we have backtracked, and we have two options when we compare it to the uh, the nearest splitting plane, the distance this of the splitting plane and the best distance. So if the distance to the splitting plane is bigger than the best distance, then the other subtree will get dismissed. Get You don't have to worry about it. You have an average case, you have some backtracking, some have to go to the other subtree, but most of them got pruned. So we still have big O log n. You have worst case uh, O of n. We could have an unbalanced tree or a high dimension tree, which requires a lots of uh, splitting plane. Next up, we'll discuss the pros and cons of this data structure. Some of the advantages is very easy to implement because it's very similar to binary search tree. And the complexity, the insertion, the deletion, the lookup, they basically very similar to a binary search tree. The next advantages is they work with any dimensional k, but as k grows, the complexity will eventually reach O of n. And this tree types, this KD tree also support many query types. I only show you one with the nearest neighbor search, but there's every other thing. There's many more that you could look it up. Some disadvantages, is the complexity go up. In this case, degrade because it's not as fast as dimensions go up. So the more dimension, the more slow it's going to be. And as of my researching, there's no automatic rebalancings like the AVL tree in the binary search tree. That's it.